Imagine watching a spaceship approach a black hole. As it nears the edge, it appears to slow, its light stretching red and fading, as if time itself is pausing. From our view, the ship seems frozen at the brink, a fading ghost. But for those inside, nothing feels unusual. They cross an invisible boundary, clocks ticking normally. Looking back, the crew would see the universe speed up, the future racing by in a flash. They've passed a one-way door in space-time, the event horizon. The ship vanishes from our sight, lost forever. This isn't science fiction. It's the reality predicted by physics. Black holes aren't just cosmic vacuum cleaners. They're places where gravity overwhelms all, and the laws of physics break down. To understand these cosmic monsters, we must look back to the origins of our understanding of gravity. Our journey begins not with telescopes, but with a simple apple falling from a tree. That moment sparked a revolution, leading us to the discovery of objects so dense they tear holes in reality itself. It's a testament to human curiosity and the relentless pursuit of answers, no matter how strange. The story of black holes is one of the greatest adventures in science. Our story begins with Sir Isaac Newton, who, in the 17th century, gave us the law of universal gravitation. He showed that every object attracts every other, with the force depending on mass and distance. This explained both falling apples and planetary orbits, a triumph of intellect. Yet Newton was troubled. He could describe gravity, but not explain how it worked across empty space. He called it action at a distance, and found it absurd. For centuries, scientists used Newton's equations to predict planetary motion and launch the Industrial Revolution, even as the true nature of gravity remained a mystery. Gravity was a ghost in the cosmic machine. But science is never satisfied with loose ends. Newton's unease hinted that a deeper explanation was waiting. The stage was set for a revolution that would change our view of the universe forever. That revolution came with Albert Einstein, who reimagined space and time as a single dynamic fabric space-time. In his theory of general relativity, gravity isn't a force, but the curvature of space-time itself. Picture a heavy ball on a rubber sheet. Objects curve the sheet, and others follow those curves. The sun warps space-time, and Earth moves along that curve, not pulled, but guided. This elegant idea solved Newton's action at a distance. The sun tells space-time how to curve. Curved space-time tells Earth how to move. The universe became an active participant, not a static stage. Matter and energy shape space-time, and space-time shapes their motion, a cosmic dance. Einstein's theory made new predictions, like Mercury's orbit, which observations confirmed. Suddenly the universe was stranger and more beautiful than we'd imagined. General relativity revealed a deeper truth about reality, but it also hinted at even stranger possibilities. Among them, the black hole. In 1915, Einstein published his field equations. They were complex, but soon Karl Schwarzschild found the first exact solution. His math described space-time around a spherical mass, like a star. For most objects, it matched Newton's gravity, except for one bizarre prediction. If enough mass is squeezed into a small enough space, space-time curves infinitely at the centre, a singularity. Around it forms a boundary, the Schwarzschild radius, the event horizon. Beyond this, not even light can escape. At first, this seemed a mathematical oddity, not a real object, but Schwarzschild's work opened the door to the concept of black holes. For decades, the idea of singularities and event horizons was dismissed. Even Einstein doubted their reality. The notion of infinite density seemed absurd, a flaw in the math. Leading astronomers argued that nature must prevent such extremes, but as we learn more about how stars live and die, evidence mounted. Supernovae left behind remnants too dense for ordinary physics. The universe, it turned out, could create these extreme conditions. Reluctantly, scientists realized black holes weren't just possible, they were inevitable. Theoretical work showed that for massive stars, nothing could stop collapse. The absurdity was not in the theory, but in our imagination. To see how black holes form, we must look at how stars die. A star's life is a battle between gravity pulling in and fusion pushing out. When fusion ends, gravity wins. The star's core collapses. For stars like our Sun, the result is a white dwarf, Earth-sized but with the Sun's mass. White dwarfs are held up by electron degeneracy pressure, a quantum effect. More massive stars die more violently, collapsing into neutron stars, city-sized but heavier than the Sun. Neutron stars are so dense that a sugar cube of their material would outweigh all of humanity. But for the most massive stars, even neutron pressure fails. Their cores collapse beyond all limits. Nothing can stop gravity's final victory. The result? A black hole. The star vanishes, leaving only its immense gravitational field. White dwarfs and neutron stars show that nature can halt collapse, up to a point. Subrahmanyan Chandrasekhar discovered there's a maximum mass a white dwarf can support, about 1.4 times the Sun's mass. Beyond this, gravity overwhelms electron pressure, and collapse continues. This is the Chandrasekhar limit. Neutron stars have a similar limit, around 2 to 3 solar masses. If a collapsing core exceeds this, not even neutron pressure can stop it. The core shrinks endlessly, forming a singularity. The black hole is born. The star's matter is gone from the universe, leaving only gravity behind. Chandrasekhar's insight revealed the true birthplace of black holes. The singularity is hidden behind the event horizon, the point where escape velocity exceeds light speed. Nothing, not even light, can escape from within. To an outside observer, objects falling in appear to freeze at the horizon, fading and reddening. This is gravitational time dilation. Time slows near the event horizon. For the falling object, nothing seems unusual as it crosses the horizon. But once inside, escape is impossible. Space itself flows inward faster than light. All paths lead to the singularity. As objects approach, tidal forces stretch and tear them apart. Spaghettification. The journey ends at a point where physics as we know it breaks down. Black holes are the ultimate one-way door in the universe. They challenge our understanding of space, time, and reality itself. Schwarzschild's black hole is just the beginning. Most stars spin, so real black holes rotate, described by Roy Kerr's solution. Kerr black holes drag spacetime around them, creating a swirling ergosphere. Inside, nothing can stand still. Everything is forced to rotate. The singularity becomes a ring, raising wild possibilities. Could it be a gateway to another universe? This idea connects to wormholes, shortcuts through space-time allowed by Einstein's equations. A white hole, the theoretical exit, would only let things out. But these remain speculative. No evidence for traversable wormholes or white holes exists. Black holes continue to challenge and inspire, hinting at mysteries yet to be solved.